Hello. Today I'll be discussing Lab 4 titled Magnetic Barking with Faraday. The purpose of this experiment is to observe, model, and analyze the time-varying magnetic field created by a bar magnet falling through a conductive tube of aluminum foil. Specifically, we will be applying the following fundamental principles to conduct our analysis. First, we have the rate of change of magnetic flux given by this expression. We also have that the magnitude of this expression is equal to the EMF, which is equal to the current I times resistance, which we can manipulate to solve for the current. Here we have the magnetic field generated by a dipole on axis, where in this case our dipole will be our bar magnet. And here we have Newton's second law, which gives the net force equal to mass times acceleration, where the forces added up to the net will be the force of gravity due to the Earth, and the magnetic force due on the magnet due to an induced current. And we get the magnetic force is given by the current I multiplied times the cross product of delta L and the magnetic field. To begin with the observations, I found the north pole of my bar magnet using a magnetometer app. Afterwards, with the north pole facing downwards, I dropped the bar magnet down a vertically aligned aluminum foil tube, the dimensions listed here. Also listed is the average time delta T the magnet was in the tube, which I got by analyzing the video using the app tracker. I'll be comparing this time later on to the time in my model to see how accurate the model is. The model was created using key data from the observations along with the equations discussed in the introduction. Here's the visual. And just to run through the code, I can go over some of the key aspects. Here I just set important physical constants we use throughout the code. Here are the dimensions of the tube that I showed in the earlier slide. For the properties of the magnet, this is the same magnetic dipole as the last step because they use the same magnet. Initial conditions times 0, the velocity of the bar magnet is 0. Here I have two functions that I'm going to be using for my calculations to be reiterated over. First is the magnetic field of a dipole. So this is based on the equation that I discussed in the introduction. And here we have the magnetic flux, similarly also based on the equation in the introduction. Here's the while loop where the calculations run through. Each iteration, we record the addition of delta T as time goes on with the bar magnet falling down. Here's the calculation for the force of gravity. And then to get the magnetic force, what I did is I used a for loop and dividing the tube up into several rings and calculating the magnetic force due to each of those individual rings, where the magnitude of those magnetic force is equal in magnitude to the magnetic force due to the bar magnet by Newton's third law. Here's the net force calculation with both the forces on the magnet, and here's the updated position velocity. One more time, you see a visual. Here we have the different colored rings representing the current flowing either clockwise with the blue rings or counterclockwise with the red rings. Here's the velocity versus time grab and the calculated time per second of C2. Right. Looking at the velocity versus time grab, we see a downward sloping and almost linear curve, indicating that our graph is accelerating in the negative y direction due to the force of gravity. This means that the acceleration also is never 0, or in other words, the magnitude of the gravitational force is always comparatively larger than the magnetic force. The next key result we have is of course our delta T's listed here, giving us a percent error of 25.26, which is reasonable. Now to close things out, let's consider the following what-if questions. First, what if the resistivity of the conductor were reduced as close as possible to 0? In this case, the induced current, and as a result, the magnitude of the magnetic force, would increase, causing the magnet to fall slower. And for the second question, what if holes or slots were cut into the tube? This would have the opposite effect. Resistance would increase, causing the induced current and magnetic force on the magnet to decrease. Thus, the magnet falls faster. And we see this relationship with these two formulas we discussed in the introduction. And with that, thank you for watching. I hope you all have a great day.